So hi, I'm Dave McAllister. I'm the strategic technologist for Scalyr. Scalyr is in log search and management. This is the only commercial portion you're going to get during this entire talk. We search log files at 1.5 terabytes per second. We have no keyword indexing, so fast, simple, and scalable. That's our basic model inside of here. What I'm going to talk about today is a topic that's becoming more and more of interest to people on distributed tracing and sort of where it came from, as well as some of the constructs and pieces behind it. This is a fairly introductory talk. If anybody wants to go deep into this, I can be bribed, particularly with good Guinness. So as we move forward inside of that. So with that, start off with one of my favorite lines. Abstractions make things easier, which makes things harder. This applies a lot. You hear this a lot in the cloud. And in fact, the original phrase is, the cloud makes things easier, which makes things harder. As we abstract away pieces, or as we add additional abstractions, we create more distributed models and distributed systems. We have more places for things like latency to come up and bite us. The problem is that latency is one of those things, to quote John Massey, a computer scientist I worked with back at SGI, bandwidth costs money, latency lives forever. So if you can control the latency aspects and not have to be limited to the speed of light, or if you are limited to the speed of light, you want to get as close as possible. So abstractions make things harder. The question is where things went wrong and what went wrong inside of that. So world is not getting simpler. This is, loosely speaking, the front end of an e-commerce system attached to the back end of an e-commerce system. And there's a ton of different pieces and services inside of that. You're probably familiar with the concept of APM, Application Performance Monitoring. This is the new category. We need services performance monitoring. Tracing will give us the first step in that pathway. And obviously, connected systems are really complex. A distributed system is one where the failure that occurs happens someplace you didn't even know you were connected to in the first place. And tracing will also help you identify where those pieces are inside of here. Interesting enough, Lamport wrote this in 1987 before things got really complex and we were worried about things like microservices, Internet of Things, transports, all those different pieces. And it's still as true today, it just happens a whole heck of a lot more often. So, observability is one of these phrases that you can hear a lot. Observability is basically monitoring on a Chuck Norris setting. It's how to look at deep pieces inside of here. The reason that this is up here is that observability really encompasses, to be honest, what are called the 4 golden signals. And the golden signals break down into events, into logs, into traces, and into capacity. And you need to be able to look at all 4 of them to truly be looking at a system. Otherwise, you're going to be able to do this, my favorite quote from Sherlock Holmes. You see, but you do not observe for here. And if all you're looking at is one of those things, you have no idea what's going on underneath. This is like diving into the pool without knowing how deep it is. So be sure that you're actually looking at all of those pieces. But today, I want to spend some time particularly talking about the tracing aspects of this, and the fact is that it's not one-dimensional. For those of you who are not maybe geometrically challenged as I am, that actually is a tesseract. So anything that slows you down is bad, so keep those all in mind. So logs, tracing, dashboards. But we're going to talk about this. Observability is a signal-to-noise problem. You start off with, we have a log category, a tracing category. But data comes in randomly. Data does not come in nice little chunks for you. In spite of the fact that people may tell you about how great their structured code is, the problem with structuring code is that you may not get all the information that you originally had in a raw data file, in an unstructured set. So you've got to be able to work with both sets of environments inside of here. I'm going to focus on tracing, mainly because I like it for here, but you actually then bring it into how you compute to it, and both in a ad hoc basis as well as in a recurring basis. Signal to noise is the issue that happens inside of observability. Don't get lost in the noise. Tracing, by the way, will give you a whole heck of a lot of noise. And so we're going to look at ways that people are refining that noise. So distributed tracing is wrong. It should be distributed request tracing. You can only trace things that are unique. So every single trace has to have a unique identifier to it. It can be something as simple as the customer request ID in an e-commerce transaction. It could be as complex as one of the emerging standards for tracing, distributed request tracing concepts. But it has to be unique. And once you have a unique identifier, there's all sorts of interesting data you can do without going off into the deep end, without having to necessarily re-instrument everything in the world. So tracing and logs do fit together, but tracing is high volume, high cardinality. It compares to log search. Tracing will tell you when things are not running correctly in a pattern match environment. Tracing does not indicate what went wrong. It only indicates that something may be wrong. And the logs at that same point in time allow you to dive into what went wrong. None of these solve your problem for you. That's still your job. Metrics is another way of looking at this. The monitoring capabilities, Prometheus, for instance, will indicate that something may have gone wrong. It'll indicate a time that it thinks something went wrong. It does not show you what went wrong. The truth is still in the logs, whether we like it or not, because as we all know, nobody reads log files for fun. So its entire concept is around bringing these events together. I knew that was going to happen sooner or later. The entire concept of this is bringing these things into causal order. And so when you have a distributed trace environment, you're actually looking at all these little events that happen with all the little segments, and you want to put them into the performed order that they occurred with the length of time that they occurred inside of here. You want to know when something is slow and what went slow. Not only just inside of the larger picture of the service, but actually inside the service itself. You still want to know what's going on inside of that. And then you want to be able to, in a sense, look at it visually. This is a waterfall plot that's up at the top here, slightly different version of that, or even find out down to the root cause analysis. Keep in mind that a lot of what I talk about is built on this concept of scale around services. Whether it's a serverless environment, somebody else is providing the service, whether it's a service and mesh environment, such as working with Istio, or whether it's microservices that you built completely yourself. These are all really important. If your problem is single-threaded and monolithic, you probably don't need distributed tracing. You could do an old technique like wolf fencing and put in little printf statements that say, hey, I've gotten to this point at this point in time. When life gets complex is when you're going to actually look at distributed tracing. In a sense, this is a way of how you aggregate logs and metrics together. Rather than looking at the endpoints, you're now looking at the passage of time in the middle of these two pieces. So, terminology-wise, first thing, you'll hear a span. A span is the shortest and smallest interval. Spans are the things that measure from your instrumented points. And a span can be an HTTP request. It could be a database query that's coming here. And for instance, in databases, you'll see a query, you'll see a fetch, you'll see a complete, you'll see all these different pieces. And each one of those is its own unique span inside of here. And each span can have multiple sets of doing this. There are lots of ways of doing distributed tracing, unfortunately, and there are companies that have built their own distributed tracing models. But those things all suffer from the common thing is that when you add something new to it, if that service doesn't use your tracing model, you can't combine the traces. And so you've got to make sure that you're dealing with that. So spans, you'll hear a lot about spans. You'll hear a lot about span IDs inside of this. My slide's out of order. Sorry. Span elements. Span ID, we just talked about, it's the unique identifier within the trace, not the trace identifier. There's a trace identifier as well. The trace ID is the trace. It is the start to finish of that request. Every trace ID is unique. Span IDs are only unique within the trace ID. They can be reused. That's a pair that crosses those two things. There's a parent ID, which said where the calls came from, what the descending order looks like, and there's a set of labels, which are key value pairs, which could be whatever you want to. Inside of this, you'll have this thing called a span context. The span context is a set of values which just get shipped along for the ride. In our world, we ship log files. The raw log is part of the span context because the raw log has information that's important to understanding what's going on inside of that trace environment. Those logs provide this unique WTF moment. So getting to the WTF as fast as possible is really what this is about. So by combining these together, we can go from identification to root cause analysis as fast as we possibly can. So I talked a little bit about this, but basically service 1 calling service 2 calls service 3 and service 4. Up here, it's the starting call. There is no parent ID. It calls down. Parent ID 1 refers back to service 1. It's call point. Parent ID 2 refers back to service 2. That's for viewpoint. If you notice, the trace ID stays the same, and the span IDs change on each one of these. Very simple element. This is a very simple model of doing this. Multiply that times something like the FAA's new data services. All microservices, all planes track that data inside of there. And you have about 2,000 of those running for a single transaction. So all of a sudden, life can get really confusing. Laser doesn't work. By the way, are there any cats in the room? So tracers add the logic. So we've been talking about tracing, and now we're switching to talk about tracers. So tracers add that unique logic that creates that unique ID. And it is generated the first time the request is made. Tracing requires instrumentation. It doesn't happen for free. So you've got to do some work to be able to get this in the set. Spans are generated when the request arrives at the service providing it. So inbound, it will create a new span ID. That span ID is actually coordinated to all of the others that have that same trace ID. So you've got to make sure that things do work correctly inside of that. Tracers work with your production apps. Yeah, you can work on debug and so forth, but tracers are what the pieces inside the production app who actually provide the information that's necessary for you to do this. You still need logs. Logs, interestingly enough, are the original instrumentation. People forget that logs are a form of instrumentation inside of here. They do provide those unique details. They determine the why inside of that. By the way, the little bird here is a play on an Australian log runner. Australian log runners are uniquely and efficiently adapted for search. So I like to play on my little log runner thing. So tracers go with this. You'll also hear the next topic, which is called B3 propagation. And this is how we pass data from one span to another using its trace ID. And inside of that, you'll see a lot of things that I've already talked about in here. The trace context, that's the stuff that's just along for the ride inside of here. The trace ID, the parent ID, the span ID, and then if you are doing sampling within that, that's where the sample counts will actually live inside of here. That's extracted into a request header, in this case I'm using HTTP, and sent back to the server span. So we have a client span to a server span. The piece that's sent into the middle, that's the trace stuff, is just the stuff in the middle. B3, as you can see, came out of Zipkin. Zipkin was probably one of the first of the distributed trace environments. Big Brother Bird was a name, but Big Brother Bird is too hard to say, so it became really quickly adapted to become B3. So, talked a little bit about how lots of companies do that. So the question is, do we need a standard to do this? And the answer, very honestly, is yes. We have applications that are written in lots of languages. We actually have services that you may be receiving from your cloud vendor that you have no idea what they were written in the first place. We can't write our own tracing for each one of those pieces. And so we need a common set of standards or common set of protocols to be able to share that information through these various pieces. And unfortunately, like every other standard, having open source geek standards wonk in my history, for this. There is no such thing as all standards merging together to one. There is just yet another standard that appears inside of this for this. The nice thing is that if you follow widely adopted standards, you get to avoid vendor lock-in, which is actually pretty important inside of this space. There is nothing quite as lock-in as having your distributed tracing, where you've re-instrumented all of your code, and then all of a sudden somebody changes your vendor and you get to re-instrument all of your code. Trust me, instrumenting your code once is more than enough, especially for anything that's complex inside of this. So let's start with the ones that exist today. Open tracing. Open tracing is a project in the Cloud Native Compute Foundation under the Linux Foundation auspices. Open tracing is pretty much been around for a number of years now. It is widely popular, but it does have some limitations inside of here. You'll see the same set of languages inside of here. We still have spans, and we still have structured data that's recorded in the span. We still have the span context inside of here, and we still have tracers that plug in for the open tracing environment. Open tracing is just an API. There is no engine. So you've got to be able to plug the data that's coming from the traces into something else that knows how to interpret that, how to build the waterfall plots, how to show you and how to allow you to do these things. Think of this pretty much as, I'm going to hand you a bunch of structured information. What you do with it is your problem. And that's really where this comes into place here. Some similar concepts and baggage. You'll hear this thing only in open tracing about baggage. It's stuff that gets carried along for the ride inside of here. And tracers can be anything that plug into this API. Popular ones are Jaeger, Zipkin, Prometheus. All these different things are open source projects, and they know how to deal with open tracing environments. There are also, just as a sideline, there are also products now that are coming out, particularly in the open source space, that are of interest in building these applications that are already designed for tracing, such as Istio Service Mesh. If you're in microservices, take a look at a service mesh in particular. If you're looking at Prometheus, Prometheus itself is instrumented. So these things have become more and more important as we move on, so we can see what's going on inside of there. I'm flying through this talk here. So the nice thing about this is that the Open Tracing API is also designed for scale. And I talked about how scale becomes more and more important inside of here. So the nice thing is that the API itself doesn't care what it goes into, but it was built on scale. So it was built with things that make it really important to understand how they are. And a nice feature inside of this is that if you do already have existing implementations, you can do a crossover between your instrumentation into the API and match it all into this environment. So it becomes sort of a translator environment in this exportation inside of here. Again, the tracing infrastructure may live wherever it wants to. And again, for this, Lightstep is probably the leader. They actually created the Open Tracing API, so they probably would be considered the leader inside of that marketplace here. Again, keep in mind, your services may not be written by you, may not be written by anybody you know. And so you have things like Lambda, serverless environments. Those also are now being instrumented so that you can simply plug in and have the instrumentation for your serverless environments as well. The other major player in this space is something called Open Census. And Open Census is a Google open source project and has some significant differences. It is a rather amazing project in many ways. Unlike the Open Tracing, which is an API only, and yep, I'm going to have to, sorry, this is where my one slide got out of order. It's a common set of interfaces, and it includes exporters. So this has the ability to plug into almost anything and has the ability to display almost any of these players. And so rather than you having to worry about what your back-end exporter looks like, Open Census has built that for you already. Major difference. Not only now is my data standardized, so are the ways that I'm looking at the data. I no longer need to learn a different series, a different way of seeing things. I can now actually look at this no matter where the data is coming from and see it as a common environment. So I use this a lot as make sure your data integrity matches up. Because if you're looking at one set of tracing and you're looking at a different set of environments, they may not be anything even close to looking across. So open sensing consists of three basic pieces here. It is libraries, and the libraries you can see on the list here. I'll actually go into some of the feature capabilities of the different libraries here. It is a full implementation. It's not just an API. So there are no real competing implementations inside of here. It is an open source project and is incredibly successful. It's been adopted by a lot of the players that have already been open tracing model inside of here. And it still uses propagation. The propagations aren't something that are called on each endpoint. So it's not just an event-based model, but it's an endpoint-based model. So its granularity is a little finer than we're seeing inside of this. And because it really doesn't care, it can send the traces to anywhere you want it to. Prometheus, Stackdriver, which is the Google version for the Google Cloud. Prometheus, which is probably the most popular open source monitoring tool. If you haven't had a chance, I strongly recommend looking at Prometheus for this. Again, to Zipkin, which is already using open tracing. Jaeger, already using open tracing. Open Census can just send the data there. And so Open Census has been able to do that. Open Census also has one major advantage. It can send it to more than one place without impact. So think of it in a sense, I can data fork and send it to multiple sources at one time. And that makes a big difference in how you're dealing into that observability issue, where you're trying to figure out everything that's going on, not just the one-dimensional, the horizon viewpoint of the world. So, simple example, a viewpoint, a user has this, goes to a front end. In this case, this front end was written in Go. There's a payment node, there's a cart service node, there's a spanner node inside of here. This is the services environments. They're going off to a back end. Tracing here is HTTP. Tracing for all these other pieces is something called gRPC, Global RPC Model. Also a Cloud Native Compute Foundation project. Currently, I believe, just graduated. So it's now version 1.0 inside of that. And exactly the same model. Trace IDs still exist, span IDs still exist, span context still exist, all these different pieces exist. The difference is that the tracers are already built in. It means you don't have to worry about building them. And that's why Open Census is probably there. So since last year, it started with Java. Java obviously is the most mature of these. Java has the most outside support for Open Census. Go, it started with Go, and Go is what Google uses themselves, and therefore it's a full API set that supports everything in the world, plus things that Google doesn't tell us about inside of that. Node.js and Python all fall into place. The other languages, interestingly enough, are there and vary in how complete they are. Those languages, excuse me, those languages all support the tracing concepts, but they may not support a statistical basis. They may not support tagging. They may not all support metrics inside of here. All of them do support context propagation because it is uniquely valuable to the determination of root cause inside of here. But as you can see, what we are seeing over time is that, for instance, Node.js a year ago had 3 of these boxes checked. So Node.js has now moved all the way up and has all the boxes checked. We expect that over the next year, we'll see every one of these languages complete its checklist where it makes sense. Oh, and just to add to it, if you want to keep track of it, opencensus.io is the place to go. It's where all the documentation lives. It's where the status lives. The other place is there is a census. Geez, that's on one of my slides, but there's a place on Gitter that can actually go in and have the conversation about what's going on at any given moment with Open Census. So Open Census, when they built this, it was purely tracing. It was purely time-based information. And the time-based information, like I said, is useful, but it's not necessarily complete. And so what we're working on now is a logging spec. And the logging spec is basically how do we correlate between the trace information and the log information that the application or services is writing off. I'll pick on Kubernetes. I spent a lot of time in the Kubernetes world here. Kubernetes, with its 4 levels of abstraction, you have an orchestrator, you have worker nodes, you have pods, you have containers. All of those produce log information inside of this. The trace information that you see is usually your application basis or your service basis, but not your abstraction level basis. And so one of the challenges is how do we tie the time frame from a distributed trace model into the abstraction level? And one of the ways that we're looking at this is through this logging structure. So we want to be able to correlate logs across all levels of abstraction to the trace content. Those logs, and they're basically going to be through a tagged API model inside of here. We want to have the agent pull in all the information, first party through third party, on the log information that's of interest for this. And then we want to have this so that people can understand how to write good first party log statements. So not necessarily replacing logging frameworks, but enhancing logging frameworks so that the log frameworks themselves now understand how to pass trace information across those various players. So the nice news, I gave you the 2 leading contenders, Open Tracing and Open Census. They're getting together. So what's been going on since about officially January, really started in December, is that Open Census and Open Tracing have agreed to get together, a full merger between the 2 projects for here. It will be a single community, and it will standardize a single set of integrations inside of here. It's not going to be one name or the other. It will be a new name. It's not a new project. It'll just be a new name to reflect the new combined environments. The good news is that you already are using Open Tracing. You won't have to rewrite or re-instrument anything. It'll just use the Open Tracing API. If you're already using Open Census, you won't have to rewrite anything. It'll use the Open Census API. And if you're getting started, you won't have to choose. So that's the nice pieces inside of here. The 2 things together are going to bring the 2 most active communities on distributed request tracing together so that we can actually make it better for everybody inside of here. The Open Census blog has a tremendous, opencensus.io again on /blog, has a tremendous amount of doing this, and the Google people, not me, will be talking more about this at KubeCon EU. It's coming up in a very short time frame here. So, if you want to play with it for yourself, there's actually a fully functional demo that's already put into place. And down here at this microservices demo is what's called the Hipster store. And the Hipster store, come on, go away, exit. Come on, whoops. And it's not going to let me get there, is it? So this is the Hipster store. And the Hipster store is a totally fictitious store that Google put together purely for the sake of being able to put something together. So it's a e-commerce model built on microservices. The microservices vary up and down on how much you're actually running inside of here. It is completely and fully instrumented. It is completely and fully open sourced. You can grab it and build it. On my Mac, it takes me about 2 minutes to build it and have it up and running. Inside of here, it's kind of not necessarily the fastest thing on my little underpowered 2015 Mac, but it's still there. And it's a great way to start looking at the code that's related as well as how the instrumentation goes together for that. While I'm in here, let's go. This is the GitHub Repository for the microservices demo. And if you notice, there's Istio, which I mentioned, which is service mesh. Service messages are incredibly important when we get to microservices. Please take a look at those as well. And then you can continue to go down and see this. So this demo, if you've never played with these products, is the way to get started. It will show you all the different pieces that are in place. Again, grab this, build it, grab something like Prometheus, Jaeger, or Zipkin, play with them, look at the code to understand how they were instrumented. You'll actually be impressed by how easy they are to put in place, and continue on from that. Oops. So, how to get involved? Well, for Open Census and now the combined projects, that was interesting. Sorry, y'all have no interest in the fact that my meeting is going on right now. If you want to get involved, the two places. Census.instrumentation has Open Census. It is the entire source code base and all of the languages. So github.com Census Instrumentation does that. Likewise on Gitter, Census Instrumentation is the active discussion that's going on. There is also an open community meeting every 2 weeks. Anybody can come in, join, and find out what's going on. Google runs that meeting, and it varies somewhere between about 20 to 25 people every 2 weeks get together and talk about what's happening inside of Open Census and where we would like to see it go. For instance, that's one of the reasons that logs came into play, is that it was obvious that while tracing information is really important, we needed to be able to go a little deeper than that. These are technical meetings. These are not marketing, there's no sales involved. These are literally purely technical meetings. But that's the best ways to get involved here. So, I have 2 questions that come out of every time I do this talk, and so I'm going to cover both of them so that I don't have to answer them without slides behind it. 1, can I store traces for everything everywhere? The answer is if you've got a whole heck of a lot of storage space. Traces are dense. They take an amazing amount of space. There's a huge amount of data inside of those. And they have what's called high cardinality, so they don't compress well. In terms of cardinality, you can kind of think of this as that columns have things that are not duplicates. Inside of a database structure, columns are unique values. Keep in mind, I told you early on that distributed request tracing must have a unique request. So you can guarantee at least one of your columns has to be unique on every single entry. Every single entry must have a unique request ID. So cardinality is a big deal. It is not unusual in a traced environment to have a single transaction request, which is a 7-step request, have over 80 unique tracing pieces, spans. Nothing at all unique about that. I've seen some that go to 200 spans just for a single request transaction. So this is high cardinality data. So when you're storing this, keep in mind that storage unfortunately costs money. If anybody's on AWS, do the pricing for an SSD drive at 10 terabytes and tell me what the cost looks like. So keep in mind. The other thing is that when you're doing this, you're going to be writing a whole heck of a lot of data. This is a high write throughput. There's a fair amount of read that happens, but reads to writes outnumber them by about a factor of 5 because you don't do the analysis as often as you're writing data inside of here. Things like InfluxDB, designed for time series information, even Cassandra, MongoDB are much better than your traditional databases if you're storing this data. Columnar NoSQL databases are the way to store this type of data. It is structured into a columnar approach to begin with and doesn't require munging to do those. So keep that in mind. Question number 2, I already logged stuff. Isn't that good enough? Well, the answer is for about 60%, yeah, it is. Because you're already doing this stuff. It's already instrumented inside of here. Is it as exact as what happened with the distributed tracing? No. But it's going to take you time to re-instrument your application. So while you're doing this, you can start doing tracing structures with your current existing logs, if your logs are sensible, and have request IDs built into it. Any e-commerce application, I guarantee, has a unique request ID for its transaction. because otherwise you're charging some customer for somebody else's purchase on their credit card. Every single request is going to be unique. And when you do that, you end up with little things like a start, a fetch, a query. This one has an error that happened inside of here. It came back and fixed the error inside of this, invoked the next application server, and ended. There's a timestamp on every one of those, and you can't quite make it out, but there is a time in MS how long each piece took. It's exactly the same amount of data. It is not the same amount of granularity that happened inside of that environment, but it's the same kinds of data exist in every single smart logging structure for transactions. If there is no unique identifier, you can't do this. But it's basically like you get to lose 50% of your weight loss goal with no exercise. It's really the model that happens inside of that. So observability does require these deep insights. Tracing gives you something that's unique and is something that is becoming more and more important in a serverless world, in a microservices world, and in a hybrid cloud world. Tracing gives you the information about how long something took to perform. And this becomes increasingly important in times where in an e-commerce environment, 5 seconds means somebody walked away from their shopping cart, 10 seconds means they complained to their friends about you for this. So it becomes really important to understand where your slow spots are and then figure out what caused them inside of here. Integrating tool sets means that you can look into this and do deep dives without having to repeat the forensic exercise for each of these pieces inside of here. And then, very honestly, whatever you choose, and A, stay with the standard for this, and B, make sure it scales, because these environments are not going to get smaller. They're not going to get less abstract. They may be easy to produce and easy to deploy, but they're not going to be any easier to resolve when something goes wrong. And with that, if there are questions in my last 10 or so minutes, I'd be glad to take them.